Hey, welcome to Curve Sketching. This is an exciting application of the derivative, and what we're going to do is to say, well, hey, look at these functions we've got here. They're all actually polynomial functions, and how do you know the graph of these functions looks like these here? How do you know that? You say, oh, that's easy, mate. I'll slap it on the graphics display calculator. Well, that's one answer, but as a budding young mathematician, let's find out why all these curves have the lumps and bumps they do here using the derivative. I guess this one up here, you'd say, oh, well, that's not too much of a problem, mate, because this is a vertex form, and we know, therefore, the vertex is going to be at 2, 1. Do you remember why? Well, maybe you could think of it as a translation of 2, 1 from the graph of x squared, which looks like this, and just moved it across. That's one interpretation of that. So yeah, well, quadratics are well known to us as being a gateway to polynomials early on, and just the squares there, starting off at low power, because a polynomial is poly meaning many numbers, many powers of the variable. So the first one, really speaking, I guess, is a linear function, but we usually say the quadratic, and then over here the cubic, and so on. So as they go up in powers, they get quite interesting, quartic. And the graphs get interesting. So let's have a look at that. Let's come over here to the cubic, and let's just have a look at the tangents here. If I was drawing tangents, can you see what's happening? Because drawing tangents is about calculus, isn't it? I think so. And then, what's happening to the tangents here? What's happening? Well, here the slope of the tangent is negative. Just remembering, review now. Lines going this way on the Cartesian plane from your year 9 and 10 work have negative slopes. Lines going this way have positive slopes. So what's happening? Going from a negative tangent, there's a flat one, so 0, to a positive slope of the tangent. Hey, that means f dash x, the derivative which measures the slope of the tangent, should enable us to map the lumps and bumps of any curve. Now what we'll have to do, of course, is one of the crucial things will be to find where the value of the derivative is 0, because that will be a point at which it will change sign from negative to positive. Okay, going to turn around, and that's usually true about a function. It only goes from negative to positive after going through 0. There are some exceptions, and we'll come across those later on. But let's use that idea now. Let's map the behaviour of the function using the value of the derivative, in particular looking at when it is 0 and whether there's a sign change around there. So let's go down now. Have a look at what we've got here. This is from Hayes and Harris, and it's good to have that book close by there, and I'm using screen clippings from there. Let's have a look at what they're saying here. We're talking about whether the function is going up or going down, increasing. Okay, well, let's look at what we understand by that. What we understand by that usually is we discuss what happens to a function as x increases this way. So if the function is increasing, we would say, well, as x increases, y would increase. Like that. That would be reasonable for an increasing function. And what can you say about the slopes of all the tangents here? They would be positive. Therefore, over here, Hayes and Harris have said the value of the derivative is greater than or equal to 0, or positive for an increasing function. What about a decreasing function? The slopes of the tangents are all going to be negative. So if a function is decreasing, remember, we're talking about as x increases. We always talk about the response of the function to an increasing value of the variable. Then the slopes of the tangents here will be negative. Can you see that both regions have included the equal sign? Both regions. Now, how can that be so? Well, let's have a look. Let's take an increasing and then decreasing situation. So over at this point, f dash x is 0. The slope of the tangent would be parallel to the y-axis. So over on the left here, f dash x would be less than 0, and over on the right, f dash x would be greater than 0, because the tangents are positive. I've got that around the wrong way here. Let's just do that again here. So this is going to be greater than 0 because the slopes are positive, and f dash x less than 0 because the slopes are negative. Okay, so we've got an increasing function over here and decreasing over here. And what we say in the middle is that's a boundary condition. Now, we include that in both regions, increasing and decreasing usually, because that's where they overlap. If you want to say is it strictly increasing, you drop out, or strictly decreasing, you do not include f dash x equals 0, the boundary there. Okay, so that's the subtle difference there. If you just say increasing, then you go right up to the boundary and decreasing and include it. And that's what Hayes and Harris got over here. So that's just a subtle point. Okay, so find intervals where f of x is increasing or decreasing in this problem, coming back over here now. Can you see that the slope of the tangent there is positive? The slope of the tangent there is positive, so it's going to be increasing for x less than or equal to -1 and for x greater than or equal to 2. And in between, of course, the slopes of the tangents are all negative, so that explains that answer. That's doing it graphically. Now, what we want to do, however, is to map the graph using derivatives, using calculus. So we won't actually have a graph to work from, so how would we get that behaviour, that curvature change and so on? Let's go down and have a look at what we might do. Here's some more examples from Hayes and Harris. So what we could do is take the function, get its derivative, because that maps the slope of the tangent. Now, first step is to find where the derivative equals 0. We've said that before. So we take a little bit of the x-axis, a mini x-axis here, and we plot on there the value 0, x equals 0. Now, we're going to look at the sign of the derivative on either side of that. So we'll sub in -1 into the derivative, and we find it's negative there. We're doing a mapping. And here we sub in 1 from this region to the right of 0, and we'll get a positive. Hey, we've just mapped it. It goes negative, flattens, and positive. And a crucial point here, of course, is that the value of the derivative is 0 at that flattening. So this is a little, I don't mind people putting this in, sine diagram for f dash x at the end of that little bit of the x-axis. Okay, so we could say again that it's decreasing on the left of 0, increasing on the right. What about neg x squared? Well, first step, get its derivative, put it equal to 0, and x would be 0, put that on a little bit of the x-axis, label it sine diagram for f dash x, and then sub in a point, sub in -1, this time into this will give us a positive result. -2 by -1 is a positive, sub in 1, give a negative. So what we've got is a map that goes like this. We don't have any values, but we have mapped out how the shape of the curve is changing there. Okay, so let's go down and do another one now. X cubed looks interesting. X cubed, its derivative is 3x squared. Put it equal to 0, and we notice we get a repeated 0. We get 2. We get x by x, or x squared equals 0, so x equals 0 twice. Put it on a little bit of the x-axis there, label it, sine diagram for f dash x, sub in a value, it's going to be up into the derivative, 1 will be given positive, -1 will be positive because it's a square here, sub in 1 will be positive. Oh, what's happening here? Let's map it. Positive, flattening, positive. And yes, we do know that x cubed does have that look about it, and this is actually called a stationary point of inflection. Just let's call it a point of inflection at this stage, because what's happening is it's changing from, it looks like it's going to be concave there, that's concave downwards, and then it flattens and turns around and actually is convex. So in the middle it's changing curvature from a concave nature to a convex. So that's called a point of inflection, where the graph actually changes curvature. Alright, let's have a look at the last one here. And this time the derivative is more interesting. 3x squared take 3. So we're going to put it equal to 0. The book doesn't actually show that here, but we know the derivative being 0 is crucial for changing from a negative to a positive, or a positive to a negative value. So here we'll say x plus 1 is 0, or x take 1 is 0, and so x equals neg 1 or 1. So draw up a little bit of the x-axis again, put in neg 1, 1, sub in a value from this end, sub in neg 2, back in the derivative, trying to track which way the slopes of the tangents are going, sub in 0, back up here in the derivative, sub in 1, 2 now, in there, so we will sub in 0 and then 2, and so we'll get these signs here for the slope of the tangents. Let's just come down here a little bit. And so we're saying it goes positive, flattens, negative, we are mapping it nicely. Look at it over here, we're mapping it nicely. And so that's good. Now, there is a little bit of mathematics you can bring in here. Now, don't worry if you don't understand it, but here I'll try to explain. Instead of subbing in values for those regions, we could look at 3x squared take 3 and say, what's its sign pattern going to be for that derivative? This is the pattern of the derivative. Well, we know that because of the x positive number in front of x squared, this is going to open upwards, be concave up. This is the graph of the derivative now. And so to the left here, it's going to be, oh yes, the values of it are positive, it's above the axis, then it's below the axis, then it's above. So that's a way of getting these signs up here directly and mathematically without subbing in, because we can say it's a concave up or convex parabola. And we know this is 3x squared take 3 we're talking about now, and we know that it must behave like this around its zeros. So that's a quickie way, if you like, of getting that sign pattern. Let's come down and use this a little bit now. So here's a couple of functions we can work with. So we're finding intervals where the following functions are increasing or decreasing, and what generally we're trying to do is to do it without looking at the graph. So what's the first step? There's the function, clearly state its derivative, factorise it. What they've left out, and I wish they wouldn't do this, put this equal to 0, so x is equal to 0 by null factor law, or x take 2 equals 0, so you get x equals 0 or x equals 2. Draw up a little bit of your number line, put down sign diagram for f dash x, and then we've got to substitute in. Okay, substitute in a value from neg 1 into the derivative. Remember, we're trying to track the direction of the slopes of the tangents. We get negative. Then we sub in 1 in here, let's say, and we get a positive. Sub in 3, let's say, in here, we get a negative. Always substituting back into the value of the derivative, because we're trying to map which way the tangents are going. Okay, so, well, this time, of course, you could have realised that this would go negative, positive, negative, because this time this is a concave down parabola. It's negative x squared, and so we would have that pattern negative, positive, negative. Alright, so let's go over here. What are we going to say? F of x is decreasing. When is it decreasing? When slope is negative there, and increasing the other regions. But what we will be doing later on is saying it's a negative slope, so let's map it. Negative, positive, negative 0, positive, and then like that. So we can actually map out through the direction of the slopes of the tangent, positive or negative, this sort of behaviour up here. Alright, let's take the next one now, this one here. Get its derivative, factorise it, Okay, so here the biggest factor is 12x squared, and outside of x take 2. So this is going to be naught. I'd like you to put this step in. When x is naught, that's twice, because x squared is naught, means 2x's are naught there if you like. X take 2 is naught, means x is 2. So we have those two values. Again, you could substitute in neg1 into the derivative. Remember, we're mapping the derivative, so I've forgotten that. This is a sign diagram for f dash x, so you'll sub back, this time sub 1 into it, and oh, it hasn't changed sign. And then sub 3 into it, it's become a positive. Notice where there's a repeated 0, there's no sign change. So what's happening there? Well, it's going negative, flattening, staying negative, flattening, then going positive. And that's supported by the technology graph there. So when is it decreasing? Well, all the time up to 2. X is less than or equal to 2, it's got negative slope all through that region. And then it's increasing for x is greater than or equal to 2. Can you see we have a powerful tool here? This is really making us sort of understand, I suppose, what makes a function tick, how curvature and maximum, minimum and slopes are all going to change. Okay, let's come down now. I'll get you to have a go at these. Find intervals, just put it down to there. Oh, hang on, here we go. Right, so finding intervals where the function is increasing or decreasing. I want you to try and do this without technology. Probably you don't need to do all of them, but to take a few from there, maybe the interesting ones, and then try some of this batch down here. Using the derivative, put equal to naught, draw a sign diagram, map the behaviour of the tangents, and then make a comment as to whether it's increasing or decreasing. Remember, increasing implies the slope of the tangent must be greater than or equal to naught. Decreasing implies the slope of the tangent must be less than or equal to naught. So using that tool there then, and your sign diagram. Alright, so pause the presentation now and have a go. I'm going to just show you the solutions down here, so you can go down and scroll down and look at those when you're ready. So here we are, we'll just do the first few here down to h, so down to the end of h. I think we'll fit that on there, down to the end of h, and then let's go to ij, so perhaps go up a little bit, I, J, K and L then. Okay, so mark your work and get ready to move on. I'm going to move on now. So let's take a more complicated looking function, something like this, and have a look. It's a quartic, and we want to know when it's increasing or decreasing. First step, get the derivative. Factorise the derivative. Now we have a problem here. We want to put this equal to naught, and this is not in this course to solve when this is equal to naught. So we're going to use technology to help us. So we're going to graph the derivative this time and find one of the values. There it is there, and you could go Shift F5 or G solve for root, for a root of the equation being equal to naught, and therefore you get x take 2. Well, yeah, we still have these other values here. Now we could actually go to equimode or do root again and move across, but this question is assuming we want exact values for these points here, exact values. So then they put something here. It's technically doubtful about this being in the course, and that's to say, so the derivative up here can be written as 4 lots of x take 2. Why? Because x equals 2 was a root of the equation. We got that from technology. And then to find the other one, we're saying, well, the quadratic factor, to get x cubed, you'd have to have x squared. And to get down the end a plus 2 from up here, you'd have to have a neg 1. The only term we don't actually know is the middle term. So let that be undetermined. Let's call it ax. And then what we do is to multiply all that out. 4 by x take 2 by x squared plus ax take 1, and if we do that, oops, let's do it all in one step here. X by x is x cubed, x by ax is ax squared, x by neg 1 is neg x, neg 2 by x squared, neg 2 ax, and then of course plus 2 on the end. So grouping that up, we've got x cubed and the ax squared terms, we've got a take 2, lots of that, grouping those up, plus x, and in that we've got neg 1 take 2a plus 2. So if this is going to equal our original cubic up there for the derivative, a take 2, let's go across up here, how many x squareds did we have? Is neg 3, and how many x's do we have? Come over here, we've got 1, so neg 1 take 2a equals 1, and so adding 2 we'll have neg 1, and does that agree here? Yes, a equals neg 1 would work there. So we've actually been able to do this work. I haven't shown all the working there, but we have been able to do that work by finding that quadratic there. So here we have it. The quadratic has got a as neg 1 in it, and that's sitting in there. So now the derivative is naught. We can get, when this quadratic has a solution, we need neg b plus or minus square root of b squared take 4ac over 2a. So we've got the exact values here. So if they didn't ask for that, you just use technology to find those, but they've done it the hard way there, or the fully mathematical way, and this part here is not in the course, strictly speaking. So let's have a look now at drawing a sign diagram. So I suggest you label sign diagram for the derivative, so it's clearly labelled. This is a bit of the x-axis. What's the lowest value here? It's neg 1 take root 5 on 2. You have to check that on the calculator. The next largest value is 1 plus root 5 on 2, and then you've got your 2. So let's map out by substitution in these values here. We've just got to go up a bit there now. Slipping away there. Let's go back through this and just get it right. Okay, so here we have our value here. So subbing in a value from out here, and what value is that going to be? Well, you could take something like neg 2, neg 3, and then a value between the two. So you have to work out on a calculator about how big these were, subbing each value you choose from the region into the derivative, sub it into the derivative, find the signs here, and then between those two, and then number 3 or something. So we've got the pattern there. So over here, let's draw what's happening. It's going from a negative slope, flattening, to a positive slope, flattening, to a negative slope, flattening, to a positive. So that's what we've got there. Now there's an interesting thing here, and I'll just stop that flicking a bit here. That doesn't sort of agree with this, does it? Let's have a look. It's supposed to be negative, flattening, positive. Hang on. It's supposed to be down here like that. What's happening here? Well, I've used the Casio over here to show you that that is not flattening there. That is not a point of inflection like with x cubed. It actually has a small max, then a flattening, and then a min, because coming down here, that's what we've said it should be. There should actually be, what, 3 turning points. Okay, this one here, and then as we come into this region, that's got to be a max, and that's got to be a min, according to our patterning of our signs there. Okay, so that's a complicated function, and we've done very well to handle that. Let's come down and have a look now at some for yourselves there. Here we are, just come in there. So find intervals where this is decreasing. We're going to do quite a bit of this work with different functions now, so there's no new concept. The same concept, but it's going to get harder because the functions are going to get more interesting, if you like. So I want you to pause the presentation there now and see what you think about I do all three of these, because you see they're all quartics, so they're interesting enough there, and have a go. All right, so pause it. I'm going to go down below now and show you the answers. Okay, so here are the three answers to A, B and C. So then away you go and see what you think, mark your work and just have a look. They are more difficult functions, and I would check the graphs using technology and just have a look at how good you were at plotting the lumps and bumps, or detecting where the lumps and bumps occur. Okay, so continuing on now, here's another type of function. Can you see what we're doing? We're doing different functions. This time it's a rational function, a ratio of two functions, and they ask you to find the derivative and show that it comes to that. So with a show that, be very, very careful that you're showing all the steps. So this is going to be the quotient rule. They've put that here. So it's the derivative of the top line by the bottom line. I'm going to come in here by the bottom line unchanged minus the top line unchanged by the derivative of the bottom line all over the bottom line squared, if you like. You remember the rule. U dash V take U V dashed over V squared. Alright, so now we need to do some simplification here, just follow it through, and of course we want to find where the derivative is 0, so we'll just go more slowly there now. Let's find where the derivative is 0. So they've left out some steps here, putting this equal to 0. A quotient is 0 when the numerator is 0, so x take 5 equals 0, or x take 1 equals 0. So x equals 5 or x equals 1. There's an important point here with a sign diagram for a rational function, and that is, see them down here, they are going to give you vertical asymptotes, and just remember the parent of these rational functions is 1 on x. Okay, f of x, y, let's call it y equals 1 on x, and it goes from being a positive above the axis and negative here without actually crossing the axis at its asymptote. The asymptote here is x is 0. So we should put on any sign diagram for a rational function, we should put the values of its asymptotes, neg 1 and 2. They should go on there as well. Alright, so we have on there 1 for when the derivative is 0 and 5, and we should just mention these should be dashed lines. They're slightly dashed there, dashed lines to show that the function doesn't exist there. Okay, so it's an asymptotic function, and then the sign diagram for the derivative, and we're going to map what's happening in every one of those regions. So you can substitute values into the derivative, so use this form, substitute values in, and see if you can map out the function, including where it's asymptotic to the line x equals neg 1 and x equals 2. And just remember, do you understand that? They are asymptotes, lines that the function approaches, because you can't have x take 2 equal to 0, and you can't have x plus 1 is equal to 0. Otherwise the quotient can't divide by 0. Quotient is undefined. Okay, so you could then see where it's increasing or decreasing. So here's the summary. It's increasing from 1 to 2. Yep, that's that little bit in there. And also then from 2 to 5. There it is there. And decreasing in these other regions outside there, and in here, and outside there. So we're getting a good picture, aren't we, of some of these trickier functions. So are you impressed with the skills you're building up here, all through the derivative? Remember, the derivative gives you the slope of the tangent, or the instantaneous rate of change. Here you can see we're focusing mainly on the slope of the tangent property. Come down and have a go. Okay, so I've got some here for you. Question 3, just see if we can get it all on there. Question 3. and we haven't quite got question 3 on that. Oh, okay, so we'll just come back to there. You have to pause the presentation, have a go, and then we'll bring the rest of it down now. So D, okay, and then we've got question 4 here. Slightly different functions. So you might have a go at all of them, or perhaps just a few, and just hone up your skills there. So pause presentation, finish that off. I'll go down with the solutions here now. So here we have 3A, B, and I think I'll have to do there, and question 4 is there. A bit more complicated with the derivative now, because it's a quotient. Let's go down to C and D, and we've covered 4 from before up here. Okay, so mark your work, toggle backwards and forwards and study the solutions. Let's move on now. Okay, so stationary points. Now, what's a stationary point? We've already covered that, haven't we? Is where the derivative is not. Why is it called a stationary point? Well, just let's observe what's happening. At that point, the derivative is 0. Now we're switching in with the word stationary. Stationary, we're switching to the other part of the trichotomy. F dash dash, or the value of the derivative, gives you the rate of change. Oh, that's where we get stationary. Because if f dash x is 0, its rate of change. Its rate of change is 0. Switching back, and therefore it's stationary. Nothing happening, if you like. 0 rate of change. So we're actually switching back to the other interpretation of the value of the derivative. So here we have, when it flattens, we're going to call that a local maximum. Why is it local? Well, eventually the function goes past that maximum. And a local minimum, why is it local? Because eventually over on this side, the function goes down past that value. So here you can see we have a sign diagram, slope sign diagram for f dash x, I think, is preferable. We can map it, positive, flattening, negative, flattening, positive, flattening, oh, and positive. Nearly made a mistake there, because that's one of those horizontal points of inflection there. Okay, so it's flattening. Just before it changes curvature, there it is, concave to convex, concave down. Okay, so let's have a look at what we can do with that then, that idea, and summarise it. Okay, so what have we got? Local maximum means it's going to be positive, flattening, negative, and I think this is a good idea to draw these in on your sign diagram, and that's the sort of shape we would get. So we can map it out like that, or with a curve. And here the idea is that we've got that. Okay, or you can put in straight lines, some sort of mapping around those values on the sign diagram. Horizontal inflection, well, you've got your 0, but it doesn't change sign. So that's one of those. It goes positive, flattening, positive, or negative, flattening, negative. So it's changing curvature. Can you see that? This is concave up, and it doesn't quite make it before it flattens and goes to down. So this is called a point of inflection because there's a change in curvature as well as the flattening there. It's a change in curvature type point. So starting to build up a summary of our advancements so far. So let's go down and have a look at a problem. Here we are, find and classify all stationary points of this one. So what we're going to do is, again, we get the value of the derivative, factorise it, put it equal to 0. Don't know why they don't put that in. X is 3 or X is neg1. So here we are, neg1, 3, sign diagram for the derivative. And they've mapped in a little sketch there. So our local max is at neg1. Sub it in, not to the derivative, that would be 0, but sub it into the original function to get its y value. So we know the max. Hey, we're now going to plot this pretty well without technology. Subbing in 3 into the function, getting its y value. So we now have the maximum point. So checking that with technology down here, there we have it. So we're doing very well here. This is using GSolve, maximum at 110, minimum there. Are you excited? We're really getting into this now. Okay, let's have a look at a different function this time. A quartic, what's the process? Get the derivative, put it equal to naught, so x equals naught twice. I guess you know what that's going to be. I think it's a point of inflection. And x take 3 is naught, so x equals 3. Putting it on there, oh yeah, subbing in here if you need to. We have negative, negative, positive. So as we expected with this repeated 0 here, we're going to have a point of inflection. So they've drawn it underneath here. We don't actually know the values of these spots at all, but we can just plot it out. So we have a horizontal inflection at naught, minimum at 3. So we should say, yeah, local minimum, so sub naught into the function and get the y value. Remember, subbing it into the function, not in the derivative this time. And subbing in 3 into the function, we get 3 neg 29. So we have a good map of what's going on, and if you use Shift F5 in the Casio or GSolve on this one, we would find those points. This is naught, neg 2, and this one down here is 3 neg 29. Okay, do you want to try? Let's try a quartic. Okay, but here we've got a little bit of revision here of what the terminology is they've asked us about before. Here we have some functions. You could try all of them. I would certainly try the x cubed ones, the x to the 4th ones, and anything with a square root in it. Okay, try those at least. Okay, so pause the presentation, have a go. I'm going to then show you the rest of these now, 4 and 5. You might watch these, you have to think about these, and this one here, finding values of a and b, you'll need 2 equations in 2 unknowns. Okay, so you've got a point there which is on the curve, hint hint, and also stationary, so it's a value at which, or x equals neg 2 is a value at which the derivative is naught, so you should be able to quite easily get those 2 unknowns and use technology to solve them. Okay, you might think about this one, cubic polynomial touches a line, has a stationary point, so your cubic you don't know, so your cubic has to be ax cubed plus bx squared, or y equals plus cx plus d. 4 things to find. Need 4 pieces of information perhaps. You've got lots of information here, touches and all that sort of stuff, so think about how you can use that. Alright, come down to the solutions now, so pause that and have a go. So coming down to the solutions, I don't think we've got them all on there quite, so just see if we can get this up there. No. So we'll go to this point here. Let's come down. We'll have to go up again now, so we'll just pause it in that position. We can. Okay, so we've got question 1, 2, A, B, C and D over on the left, 3 and 4, we'll come back for 5. So pause it, check your work, and then we're coming down to E and F and part of G and H. Pause it there, and down the bottom here I and J. Check those things out. Also check it with technology. So then we just pop in here to get 5. Okay, so go through those, pausing the presentation and checking your work. Okay, so I'm going to go on now with more functions. So let's have a look at the next one now. There's a big rational function type here. Use technology to obtain the graph. What are the function's vertical asymptotes? So here's our graph, fairly complicated. Asymptotes occur when the function's undefined, so the bottom line would be 0. You cannot divide by 0. That's a reason for that being an asymptote. Factorise it. Put equal to naught when either x plus 1 is naught or x plus 4 is naught. So they are our asymptotes. So we've answered that part of the question. Let's look at the stationary points. Stationary points mean you need the derivative, so that's u dashed v, take u v dashed on v squared again, and it's a big one. Simplifying the top line, let's check this now, simplifying the top line to 10x squared take 4, bottom line's got lots of squares, don't have to worry about that, because we now know, first of all, the asymptotes go in, neg 4, neg 1, dashed line, and to show that the function's going to approach that value, not be defined at it. Putting this equal to naught, the top line of the derivative, remember, the derivative has to be made equal to naught. A quotient is 0 when its numerator is 0. So x equals neg 2 or 2. And then we can put in, here our sign diagram for f dash x, always good to put that on the end there, and you can substitute values in and map out the behaviour of the function, which should agree with the graph above. Okay, so here the actual points, put in neg 2 into the function and 2, so we've actually got the x and the y value of the local maximum. So this is this one here, local max, and this one here, local min. So we've done a good job to actually map out this function up here. We've done very well with being able to determine where the graph lies. Okay, so let's have a go at some of those now. Here we are, question 6. Just come back up there, if we just get it here. Question 6. Probably not necessary to do all of them. Maybe just A, C and D, something like that, and use technology to see how you went. Alright, so pause presentation, have a go. I'm going to go down to the solutions now. We're looking at the solutions here. I don't think we can get them all on. So there's A and B. So I could pause that. C and D there. E and F. Okay. So pause those and see what you think. I'm going to go on now. Another problem. Now this is an important problem. Let's have a look, because it deals with the local max and min. Find the greatest and least values of that on this interval. Okay, well, they've drawn a graph first of all, and because it's y, they've found the derivative, which is now dy by dx in that notation. Factorise it, put equal to naught, either x is naught or x take 4 is naught. Got those two values. Now here, what we really usually would do would be to draw up a sign diagram for the derivative, because they usually would ask you that, naught and 4, and then go in here positive, negative, positive, working that out. So we've got this mapping like that. So this will be the local max at 0 and the local min at 4, and we then could substitute those values in. But what we're seeing here is if we're allowed to go from neg 2 to 5, you've got to check the end conditions. Substitute neg 2 in and 5 if you like. Well, 5 clearly doesn't go above the local maximum, but if you sub in neg 2 here, you will find that at neg 2 it goes lower than the value at 4. So at neg 2 it's neg 27, and at, oh no, it doesn't, it's even, and at 4 it's neg 27. So you should substitute in these values, 0 and 4, to get the local max and min, but check that it doesn't go past the max or past the min down below there. So it actually draws even. When x is neg 2 or when x is 4, that is the minimum value, which is neg 27. But do you get the idea? It's a local effect, So you should check the endpoints of the domain there, the end values of the x's, to see whether they go past. Okay, study that. What I'd like you to do now is to have a look at the couple of problems down here, 7 and 8. I'd like you to pause the presentation and have a go, and I'll go down to the solutions now. Okay, so there are the solutions. Have a look at them, and again, use a graph to accompany your work, technology to assist there, because you will have a calculator with you. But of course, remembering if they ask algebraically or without technology or for exact answers or show that, then you have to show the mathematics of it, the algebra of it. Right, let's move on. I'm just going to summarise some of the things we've done here and go back to those graphs we had earlier. Can you notice that if we have a concave curve, well, that's like this bit here, can you see that the slopes are positive, 0, going to a negative? So actually what's happening is the value of the derivative, f dash x, is going from a negative to 0, positive to 0 to a negative. That's said to be decreasing mathematically. So here, f dash x, the slope of the tangent, is decreasing. Therefore, in this region, the second derivative is less than 0. Okay, and if we come over here, if the curve is convex, goes from negative, slopes of tangent 0 to positive, is going from a negative to 0, getting more positive. That's said to be increasing. F dash x is said to be increasing if it follows that behaviour. So its derivative is positive. Remember, a derivative is the rate of change of the function. We can switch into that part of the trichotomy now. So if you find the derivative of anything, then you're finding its rate of change. So when we find the derivative of f dash x, we're finding the rate of change of f dash x. So if f dash x is decreasing, its rate of change value must be negative. If f dash x is increasing, its rate of change value must be greater than 0, or positive. Okay, so that's going to bring us into the use of the second derivative here. So let's have a look at some of that. We've got functions here, interesting enough. Let's just have a look at this one over here, in this region there, through to there or through to here. We could look at the value of the second derivative in any of those regions and have a look at where it would be increasing or decreasing. So we're going to get into a little bit more detail on these functions now. And we see here we've got, well, the interesting thing over here, let's go back over here, is can you see that we have convex in this region, and then somewhere in here you've got to turn your pen to change to concave, don't you? So there should be a point of inflection somewhere in here where the curvature has to change. Here it's quite clear, it's a flattening point, and that was convex, came into not completing the convex, didn't complete the convex, flattened and went to concave. So there was a stationary point of inflection in the middle there, but that point of inflection still represented a change of curvature from convex, that sort of upwards, concave up to concave down. So let's start to increase the level of sophistication now. Let's come down here and have a look at this function. So what we can say here is through this region, through to here somewhere, what can we say? Well, this is going from negative slopes to 0 to positive. So there we are saying f double dashed x must be greater than 0 because the slope of the tangent is actually becoming more positive. It's actually f dashed x is increasing, so its rate of change measure would be positive. So that could be another test for a local minimum. So where the second derivative is positive is a local minimum. Sort of opposite to what you'd expect. Minimum is usually small, maybe negative. But no, think of reverse association there. When it's a minimum, the second derivative is actually positive. So that could be used. Put the second derivative equal to naught to see what its signs are like and see if we can detect a local minimum that way. And then here, of course, is going to be, as I've hinted at, a point of inflection, somewhere where you have to change your curvature from convex to concave. And then in this region, the slope of the tangent is positive, 0, negative, and keeps going. So in this region here, the second derivative would be going from a positive to a negative is going to be less than naught, and that's going to be a local max type behaviour around that. Where can you see positive slope 0 and then negative is a decreasing value. When something in mathematics goes from a positive to a negative, is decreasing. So slope is decreasing, its rate of change measurer, the second derivative, is less than naught. So getting sophisticated now. Try and hang on there and maybe rewind the presentation to get on top of that. So here we are, we're talking about points of inflection now. And points of inflection are where the second derivative equals naught and the sign of the second derivative changes on either side. So let's have a look and see if we agree with that. Let's go back up now and say, well, a point of inflection, there it is. Why would the second derivative be equal to naught? Well, here we're saying the second derivative is positive on this side and negative on this side. So somewhere in the middle, the second derivative must go 0. It's got a sign change. Alright, this is a second derivative now. Getting a sign change from a positive, so that's what it was in this region over here, to a negative. So in the middle there, that point of inflection is detectable by finding where the second derivative is 0. Of course, it could be the other way. We could be turning around oppositely, like if we went like this now, somewhere in here, the second derivative would be 0. To change your pen from going down to going up, that's the change of curvature, that's a second derivative, and it represents where, what? It becomes most negative and then starts to go positive. So it's going to be a maximum point for the slope, because this is a maximum positive slope that you get at f double dash x equals naught. It'll be the maximum value of f dash x, isn't it? Okay, so where is a function a maximum? When its derivative equals naught. So these points of inflection are going to be maximum values of the slope there, either most negative or most positive. So we'll come back and look at that a bit later on. So it's got to change sign there on either side. So let's have a look at a bit of a summary now. If you took a function like x to the fourth, that's a bit confusing because its derivative is 4x cubed and its second derivative is 12x squared. And so if you look at the second derivative, it doesn't change sign on either side of that 0 when x is naught. It's positive on both sides, and the reason for that is it's not a point of inflection there, because you've got a repeated 0x to the fourth going to x cubed, repeated zeros, and there's no point of inflection just because the second derivative is naught. So second derivative equals naught usually means a point of inflection, but it need not. You've got to check if the 0 is repeated, and if it is, then it could be like x to the fourth, it doesn't have a point of inflection. Alright, for a curve which is concave, we've just said this, that is, it's got a local max. Remember, it's negative, the second derivative. If it's convex, it's got a local min, so this is a local max. And if it's got a local min, the second derivative is positive, sort of opposite to what you might expect. And then if the second derivative is naught, there's a point of inflection. It could be a flattening point if the f dash x is also 0 at that point, or it might just be a change in curvature. So let's draw those. Here are the two types where it's a horizontal. There's a flattening as well as a change in curvature. See, change in curvature and a flattening. There could be a change in curvature like this, so there's still a point of inflection there, no flattening, or a change in curvature like that. Still a point of inflection in there where you have to change your pen to turn around and make it concave from convex, or convex from concave. Alright, let's have a look and pull it all together now. Find and classify all points of inflection for this function. Get the derivative. Get the second derivative. This time we're putting the second derivative equal to naught, so x is naught or x is 2, and drawing a sign diagram for this time the second derivative. Okay, and just checking that the sign of the second derivative changes. So the points of inflection would be at naught and 2, sub naught back and 2 back into the original function. Okay, so f of 2, sub those back. This is just checking the sign of the derivative there. So we want to know whether there's a flattening. So this first one, there, f dash x equals naught. Second one, it doesn't. So the first one at x is naught is going to be, what's it saying? Like that. And then in the other one, it's going to be just ordinary change of curvature. And one of those. Now we're not asked to draw the graph here, so you could check the graph of the function to help you back up here, but what I'd like you to do is just try a couple of these, maybe the x cubed here, x to the 4th, and this one, just putting the second derivative equal to naught and seeing if you can find the points of inflection, checking with technology. Right, let's come down to the solutions there. So pause it and have a go. I think we've all got them all there now. So just having a look at what behaviour. Just remember, I would suggest use technology to check what's happening and whether you can identify these points of inflection, change of curvature. Alright, so have a go and check your work. We're going to go on now. Alright, so bringing it all together. This is a definitive question now. You must be able to do all of these. Let's take a quartic. Find and classify all points where f dash x equals naught. Okay, get the derivative. Try to factorise it now. So that's a fairly hard one there, because you've got to use that x squared plus ax arrangement. Get this, a sign diagram putting x equals 1 and x equals negative 2 as a 0 as a sign diagram for the derivative. This value here, you could use technology because it doesn't show that this is a factor. They are exact values, so you could have just put this equal to naught on the calculator if you wished, and then drawn the sign diagram. We can see here the value of the derivative is negative on both sides, so it's coming down, flattening, coming down. Not a bad idea to draw that. So here it's negative, flattening, positive, so you've got your local, you've got a horizontal inflection there at neg 2, got to sub it back into the function to get the y value. Local minimum at 1, sub it back into the y value, the f function, to get its y value there. Okay, come down a bit now. Second derivative, because we want all points of inflection up here, didn't read that. Put that equal to naught, so x is naught or neg 2, and then checking its sign goes positive, negative, positive, so this is a sign diagram for the second derivative now. So we have got a horizontal point of inflection at neg 2, that one, and 0.3 is a horizontal inflection, so therefore we're subbing these in again. Neg 2, 19, we've got that before. 0, 3 is a non-horizontal point of inflection. So change the sign at both, so the points of inflection. One is horizontal because it was from before the derivative was 0 back at the beginning there, and non-horizontal inflection. Okay, so let's have a look at increasing or decreasing regions. So fx is decreasing for x less than or equal to 1, so that's going back up here to that sign diagram for f dash x. It's increasing for x greater than or equal to 1, where f dash x is positive. So this one's less than or equal to 0, this one is greater than or equal to 0. Going back to the sign diagram up here. So where's it concave and convex? Well, we can map out what we've gotten so far. It was negative slope, then we got this point, and it was negative slope, then it was 0, and so on, and we got this point as a point of inflection. So we've done the whole graph without technology. That has been absolutely fantastic. A lot of work there, but you have your tools now. So come down and practice. These are important questions. I would do all of these questions now because this pulls it all together and doing all aspects that could possibly be asked in any question. And congratulations, you've made it to the end. You can actually draw a pretty accurate graph with limited use of technology. So hopefully you're excited about that. You know, use of calculus for you to understand graphs of functions. So pause the presentation now. I'm just looking down here at a cubic polynomial. They've given you some information here to help you. So have a go at those harder questions, more theoretical questions there. And pause it, and I'll go down to the solutions. So lots of graphs here now. Question 2. Have to pause that to have a look and see what you think. Right, go down and finish that off. I think we'll get F and G maybe in. F and part of G. G and H. And now question 3. Okay, so they were hard questions there. When you're looking at this is contracted multiplication or synthetic multiplication. A quick way, well, I don't know, there is a quick way of doing it. You might do it just by multiplying all these out. Okay, you can do it that way as well, expanding it all, and you'll get this line here. Okay, so this is not in the course, this form of multiplication. You can just do it by extended FOIL from before. Alright, so mark your work. Got a final exciting aspect coming up, and so I'll go down there now. Now this is very important because this is not in the Hayes textbook and has been an emphasis in the tests and exams as the course has developed. So let's have a look. Finding the relationship between the graph of the function and the graph of its derivative. So here I have the graph of the function, and I now want to draw the graph of the derivative. So let's have a look. Let's start here first of all. We know the value of the derivative is 0 at a turning point. So here's another turning point. So it's 0 there. Now, the slope of the tangent up here is negative. So I'm going to have to start down here, because below the axis, remember, is a negative value. I'm going to come up here, and then when is the slope of the tangent going to be a maximum? Well, that's a point of inflection, isn't it? So somewhere here I will get to my maximum value positively. See this? going positively, and then it's still positive, so it's still all going to be here, the positive slope, but it's going to be a maximum about here somewhere before it starts to still be positive but decline into 0, and then it's going to be a negative. This is hard because you're plotting the slope of the tangent as above or below the axis. Now we've got no scale here, because obviously when you differentiate you get a different degree polynomial, and it's going to be very difficult to plot them on the same set of axes. Do you get the idea? We're plotting the slope of the tangent here as being above or below the axis. Let's do another one. Let's come down. So this is the graph of f dash x is what we're trying to do there. We're trying to draw the graph of the derivative. Come down. Let's take another one here. So this one, let's do the same things. So here we have a flattening here, point of inflection. So that's going to be 0 there. And we have another local minimum. So slope of the tangent, remember, at these points is 0. And now let's see if we can map it. Slope of the tangent here is all negative, getting less negative. So we're going to come up here. Oh, hang on though. It goes 0 and then it stays negative. Stays negative, coming down here. Now somewhere in here there's a point of inflection, isn't there? And at a point of inflection, that will be the maximum value of the derivative, the maximum negative value. So here somewhere like this, then it stays negative, so still under the axis. It's coming up to 0 and then it's positive. So can you see that? This is the graph of f dash x. Okay, so we're plotting actually the slopes of the tangents as a graph. So can you see association here? This looks like a quartic, x to the 4, etc. And this looks like an x cubed. So yeah, that sort of agrees. If you differentiate a quartic, you do get a cubic. Let's go down and do the opposite. Now this is going to get confusing. I'm going to give you the graph of the derivative, so this is the slopes of the tangents, and ask you to draw the graph of the function going backwards now. So let's take this one now. So we have here, now this is positive for slopes and this is negative. So we can see the derivative comes down and is 0 there. So, and these are positive slopes. So it's going to come up, positive slopes to some maximum. We don't know where that is. And then it's going, oh, here is a maximum value for the, or minimum value for the derivative. And here's another 0 here. So we're going to come down here. This is negative slope. So we've got the slope of the function is negative, going to stay negative, and come down here. Now this at point of inflection is its maximum negative, so is that about right? Yeah, probably about right there, and then it's going to have to change curvature to come up, because there's its maximum negative, less negative here, so maximum negative slope, less negative, and then turning point there, and then it's going to have a positive slope. So can you see that? This is confusing now. I'm trying to draw the graph of y equals f of x based on whether these slope values for the derivative are above the axis positive or below the axis negative. Alright, let's do another one. We want the graph of the function now given this one. So let's have a look. Remember, these are slopes of the tangents. That's a positive and this is a negative. Alright, so in this one now, what have we got? We've got negative slopes, then it's a 0. So okay, so it's going to come down be 0 there. Then it goes to positive slopes. These are all positive slopes here, positive slopes, and the slopes get to a maximum positively, so I've got to make that a point of inflection. Then the slopes get less positive and should be 0 here, so got to be up there. And then the slope's going to get negative through this region. Yep, negative. So positive there and negative. Now when's the maximum here value of the negative slope? So they're going to start to go negative. So up here is a maximum negative, like that. Another turning point here. Okay, a maximum negative. See through here. These slopes are all below the axis, so that's the most negative it gets at the turning point. Then it's negative, at that point of inflection, sorry. Then we've got to have a 0 here, so I've gone a bit past a 0, and then the rest of these are all positive, so it's got to go up. So that's the graph of the function now. We're going backwards. Hard to do, isn't it? Have to keep your wits about you. Now we don't know where these turning points are here, so you actually can't plot those exactly. But that's the idea. I'd like you to try some now. So here, draw the graphs of the derivatives of the following functions on the same axes. Okay, so what you need to do is the same sort of thing. So I'll pause the presentation now because I'm going to write the solutions over the top of these. So therefore you need to actually have those done by the time I do that. So pause it now. Well, did you get them right? Have a look at these, and you see the crucial points. The maximum value of the function has to be a 0 of the derivative there, and where there's a point of inflection, that's going to be the maximum or minimum of the value of the derivative. So again, here we have a minimum, here's a point of inflection, so that's just a touching on the x-axis for the derivative. And this point here is as maximum positive due to coinciding with a point of inflection on the graph here. Maximum positive of the derivative. This one's a bit plainer now. This is a point of inflection. That's going to be the minimum value because it's negative. Negative slopes to tangent, negative slopes there. So we're going to have that sort of graph for the derivative. Alright, so very important. Oh, sorry, I just made a mistake there. Let's just change that. The slopes of the tangent there are positive, and so we've got these here for the function. So let's have a look for the derivative. Sorry. So let's have a look then at going the other way. So it does get confusing here. Let's have a look at going back from the derivative to the function. Okay. Here are the graphs of the derivatives. Draw the graphs of the function. So I'd like you to pause the presentation now, have a go, because I'm going to write the solutions over the top. Well, here we are. How good were you there? Let's have a look at the first one, starting with where the derivative is 0. So when the derivative is 0, going to be a maximum, because we said here the slopes of the tangents here were positive, so it's going to go this way. And then very important to realise the least value of the slope down there negatively is a point of inflection, so you've got to change your curvature there. Coming around, there's a 0 there, so that's a minimum, and then it keeps going positively. If you look at the next one, crucial point is derivative is 0 there, so that's going to be a minimum point, and I haven't done that very well. It's across there. Let's just bring that back, and because here the value of the derivative is 0, so it should actually be like this, and then it's broadened out here because of this behaviour, so it's not symmetrical about that. So here, when this is 0, that should have been, it's still cockeyed there. Here I want to put it a little bit better than that, so it's like that, and then it broadens out. Okay, so that's a fairly plain one. The one down the end here, 0 will be a minimum because here the slopes of the tangents are negative, so that's the function here. Then the maximum value of the slope of the tangent there is that point, so that's got to be our point of inflection. They're going positively, keep going positively until here, so that's a turning point, and then they go negatively to the most negative, so that's a point of inflection, before they start to turn positively again, and this is a derivative is 0, so it's got to be a turning point. So a fair bit of work there, a fair bit of work. Now these last two questions are rather challenging. You need to go back and have a look at them again perhaps. Alright, well, congratulations for getting through all of that. We've got one more application of the derivative in what's called optimization, finding optimizing the best solution in a practical or modelling problem. So I look forward to seeing you in that presentation. But for now, it's cheers from me.